Okay. Wait a moment. Okay, so for the first problem, the problem, is there anybody that wants to present for the first problem?
Oh, then you start the
like,
following, please.
What?
Oh, Zhan, please stop presenting. And also Edward, please click all eyes on me. Thank you.
Oh, okay, so does anybody want to present?
Does anyone want to share their method for the first question? I think that one is the easy one, right? I saw lots of people, got the points.
Then
Okay.
nobody wants to present. Okay, then I'll present then. So the problem states that the magnitude of a complex number z is equal to the magnitude of a complex number w is equal to z times the the w and plus z with the conjugate of z times w. So there's something you should know about complex numbers that will help you basically understand this problem. The first thing, that if a complex number, say x, is written as a plus bi, then the absolute value sign actually means the magnitude, and it's the square root of a squared plus b squared. And x with a bar on it is the conjugate, which is equal to a minus bi. So there's also some properties you might want to know for this, because it's better to do the problem with them. And the first property is that the magnitude of a number, x, is equal to the number times its conjugate. You can do this not too hard by
You mean x squared, right?
yeah.
Yeah, right.
Yes, the magnitude squared, and you can do this really easily by just multiplying them together, and you get that's equal to a squared plus b squared, which is equal to magnitude of x squared. And so that's the first property. And the second property you need to do in order to do this problem is that if you have the conjugate of two complex numbers, say z plus w, that is equal to the conjugate of z plus the conjugate of w. And this is very, very simple to prove. If you have z equals a plus bi and w equals c plus di, then this is equal to a plus bi plus c plus di and the conjugate of that, which is equal to a plus c minus bi minus di, which is equal to a minus bi plus c minus di, and that is equal to the conjugate of z plus the conjugate of w. So after you know some of these properties, we can continue on to solving the problem. So the problem asks you for the largest possible value of the real part of z plus w. And if you have z plus w, the magnitude of that is equal to the square root of a squared plus b squared. And for the rest of the problem, I'm going to assume that c plus w is equal to a plus bi just for convenience. So past this, if we want to maximize the real part, which is A, and the most common way to maximize something like this, and we know that this other value, let's say, doesn't change. If this other value doesn't change, the most common way to maximize it is just to minimize the other one. And in this case, the other one is this b squared term we have, and the minimum value of that, as we know, is 0. So we should like make b 0. But first we have to make sure that the magnitude of z plus w does not change if we change a, because we have some like very specific like conditions that we have to follow. And so first we have to see this. So the magnitude of z plus w, as I've talked before in this first property over here, is equal to z plus w times the magnitude of z plus w. I mean, the conjugate is z plus w, and this is a squared. So we can calculate this and further simplify it by using the second property to the second one and doing this. Now, in order to like make sure this is actually the correct step to do, we can look at the condition we're given, and we see we have the magnitude of z and the magnitude of w, and z times the conjugate of w and the conjugate of z times w. And we see that if we split it up, we can expand this. And it'll give us something that looks a lot like this. And we wouldn't be able to achieve this if we just expanded this one, because you can't really break apart z.
Wait, Edward, I think you also forgot the the W conjugate Z term.
Oh yeah. Because like, okay, right. Okay, yeah. So after that, you can sort of uh change this into z's, the magnitude of z squared, because that's what the condition gives you, and you want to like go back, and you just add those back, and this is 1, this is 1, this is also 1, so this is equal to 3. And we know that we now know that the magnitude of z plus w is the square root of 3. So right now we have found that the magnitude of z plus w is a constant number, and it does not depend on a. So now we can sort of assume that b squared is equal to 0, and assume that this will not affect the can somebody not do that? And assume that changing the value of b does not affect this magnitude. So we can safely let a equal, the square root of a squared equal root 3, which means that a equals root 3. And so this is the maximum, and this is the maximum real part, so our answer is root 3. Was there any questions? Oh yeah, Kaba, what?
I think you square it, right?
No. For which step?
Like it says the square of the constant.
The square of the what?
It says in the problem to square it.
The square of the minimum value.
Oh yes. Find the square of the largest possible value. So actually then it's 3. Oops. Then a equals the root 3, then a squared equals 3. Okay. Is there any other questions?
Yeah, what if Z and W are both equal to 1? So wouldn't it give you 4 as the answer and that's more?
If Z and W are both 1, then this condition is not satisfied because the conjugate of, if you can't see it, you can't see it right now. So this part is not satisfied and this equals 1.
Wait, never mind. I didn't know it was plus. No, yeah, I thought it was equal.
Okay. Is there anybody else with a question? Okay, I'll take that as a no. And I'll move on to the second question. Okay, so for the second question, is there anybody who wants to present? Kabra, do you want to present?
Yeah. Okay, so basically we have wait, okay. So we have the coordinate grid and it's like wait, how do I okay. So the coordinate grid is like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is our wait, let me just draw it. Also, what was the answer? Like the correct answer for this question?
The correct answer is 58.
Okay.
Okay. If you get
So
the answer, you can.
yeah, I got 58. So if we just draw this. So there's like a so this is where what's his name? A scout is at.
Billy Bob.
And he needs to go to 3, 2, which is over here. Just mark this at A for Atticus. And then you have to avoid the point 8, 5 and the point 6, 4. So this is basically a grid walking problem, but the twist is that you can't go to these 2 points, this and this. So how you do it is you can just basically erase. You can, oh wait, you can erase it. Those lines that connect to, wait,
Oh.
I think, yeah. And then the other point was. So you can basically wait, it was this and this, right? So you just have to avoid. So I'll just like wait, how do you can't go to this, 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 this. You can't go on these lines. And then what we can do is like if I write a 1 here, it means that there's one way from that point to A. So for this one, it's also 1. This is also 1. This is 1. And this is 1 because you have to go down. And then same with 1 here.
Are you counting from A or to A?
To A. So like
Wait, Carver, I believe like your method is starting from A to S, but we want to do S to A, but either way, it should be the same.
no, like for example, these points are the number the number of ways from that point to A.
Yeah. Okay, yeah, I think you can also do that method. But
Yeah.
then you sort of just sort of like also reverse the direction, except like now you sort of consider moving up and right.
Oh yeah, yeah.
Yeah.
So then you can just add for each point, you can add the one on the left and the bottom. So this is going to be 2, this is going to be 3, this is going to be 4, this is going to be 5, this is going to be 3, this is going to be 6. This is gonna be 10, and this is gonna be 15. And then this is gonna be 4. And then for the next point, you can't get there, so you can just like write a 0. And then for the point above that, it's 10 plus 0, so 10. And then 25 here. And then here it's 5, 5, 15, 40. And then 6, 11, and then this is 0. And then this is 40. And then this is 11, 12. Wait, I think I made some mistake. Oh, this could be a 7, I believe. Wait,
Yes, that's a 7.
yeah, that's a 7. And then this is 18. And this is a 18. And so this is 58. So 58 is our answer.
Okay, that is a good solution and a very close to the real solution. And so I want to mention that in the real solution, instead of labeling the value for the number of ways to get to A, I was labeling the number of ways to get from S to that point. So it's more straightforward, and we don't need to think, it's not as complicated. But the solution is definitely good, and so yeah, I'm going to present the other way, and I'm gonna first like clarify some things within the problem because it wasn't exactly the worded the best. So the problem says that I'll just like borrow a diagram that I drew earlier. Wait, let's see if this works. Okay, evidently didn't know. So I'm just going to borrow a diagram that I made earlier that has all of my points. Or I can draw one that's not working. It's not working. Okay. So this is my diagram. It's a little big. Let me make it smaller. Wait, how do I do that? Okay, somebody changed it for me, so that's good. So this diagram shows the things. No, I did not include the rest of the grid. And sometimes that's helpful because you don't want to draw the entire grid, as that sometimes takes a long time, and sometimes you can see that the other part of the grid is unnecessary. So I drew this diagram. And some of the things that you might not understand about the problem is that Scout has to take steps of unit distance parallel to the axes, although the problem do not specify that, but it's pretty clear from the context. And that it's also pretty clear from the context that when the problem says Scout must not see Miss Dubose, that means that Scout cannot go on to 8-5, which is where Miss Dubose is. So after that, I would use a method called path counting or something like that. And there's a few basic rules to it. Basically, you choose a starting point. In this case, the starting point is this Scout point, and you label that as 1 because there's one way to go there, and that's staying there. And you label every single other point as the number of possible ways to go there. And there's like this certain part of it which like means that every single point that you cannot go to basically is 0, since there's 0 ways you can go there, because if you go there, your path is invalid. And your final answer is the number on the last point, which is here. There are a few rules to it, not that much. So the only really important rule is that if you have a certain point with 2 other point going into it, and there's no other points, then that point, if this was a what? Am I drawing? If this is A and this is B, then this point should be labeled as A plus B. And knowing this rule can like help you simplify it and make sure that you can do it fast. And if you don't have like if you like only have 1 point going into that point, you can like ignore B, and so it's the same number. And there's a pattern in these rectangle ones where you can just like label each of these points that go in either direction 1. What am I doing? And this one 1, 2. And you can like therefore like label every single other point. 1, 2, 3, 4, 5. 1, 2, 0, 3, 7, 12, 4, 4, 7, 14, 26, and the answer is 58, as you know. 18, 11, and 7. You can, the general rule about filling out the numbers is that you have to know the numbers that it depends on before filling it out, or else, it doesn't really make sense. So as you can see, the answer is 58. Is there any other questions? Or any questions? Okay, I'll take that as a no then. So for the next problem, we have like a diagram. I can actually just draw that diagram, I think. Wait, let me. Oh. Okay, okay. So is there anybody who wants to present? I can draw the diagram for now.
I feel like a question 3 is pretty hard because I look at everybody's submission, like almost no one answered this question. So probably you're gonna present. Yeah.
Okay. Then here is a diagram. Okay, let me draw another. Make sure the diagram looks like this before I draw it. Okay. Good. Okay, so this is our diagram. Let me label the points. Points A, B, and C. And this is side C, this is side A, and this is side B. So the problem gives you 2 pieces of information, specifically angle A over angle B equals angle B over angle C. And B squared minus A squared equals AC. And there's some things I want to know about these conditions that make them very special. First of all, the first one is the ratio of the angle measures in a triangle. And this often means like this value is probably going to be known, and it's most likely going to be a specific value that you're going to see. So this is something to pay attention about, and it sometimes means isosceles triangles, and so that's something to pay attention to. And the second one it has the multiplication of the sides. And it's not area, since when they say AC, that's not the same side, so you can't make like squares. And also there's no like right angles, so like it doesn't really make sense to multiply two sides. And usually what this means, and also the fact that there's a circle in the problem, even though there's not very obviously any use of the circle right now, is that we're going to need a quadrilateral and use Ptolemy's theorem. So something about the Ptolemy's theorem. It talks about a circle. Wait, let me draw a circle smaller. And if there's 4 points on that circle, and there's like 4 lines on that circle from those 4 points, and there's like a cyclic quadrilateral. Wait, what am I doing? So if there's like so if like we have like a cyclic quadrilateral like this, and the sides are A, B, C, D. Wait, no, mine are in the wrong order. A, B, C, and D, and the diagonals are E and F. Then AC times BD equals EF. I mean AC plus BD. And so this is where our AC, as you can see, is coming from. But right now we don't have a quadrilateral, so that's kind of problematic. And also there's something that you have to know about adding auxiliary lines to make a quadrilateral, is that if it makes it more complicated and adds more variables, like a lot of more variables, that's not good, which is pretty obvious. You don't want to be solving for more things. So in general, you want to construct something symmetric, and the best idea in this case is a reflection of some sort, because the other symmetric ones don't like really work. So in this case, I'm going to reflect the point C over to the other side of the circle, although it could be almost any other point. It just seems that C is the most conveniently placed point. So like that's my other point, and I'm gonna connect it like that. And also connect this other this other line, this other diagonal, because that will let us use Ptolemy's theorem. And from symmetry, we can see this diagonal is also B, and this is A. We'll let this be X and this point be D for now. And we see that XC plus A squared equals B squared. Now we want to solve for C, and that's not actually going to be too hard in this case. And also there's something that really helps us from this Ptolemy's theorem. We see there's no AC, which is not that good, but we see that we have A squared and B squared, that if we move the A squared over, so it's XC equals B squared minus A squared, or this can turn into AC from the previous equation, and it's easy to cancel out the C from both sides and get X equals A. And now this is kind of really important, because it like tells us all the sides, and we didn't introduce any new variables. And this is sort of like a special figure because there's like a bunch of isosceles triangles, and that's really helpful. But we won't be using Ptolemy's theorem again because it's kind of useless now. We know all the sides. So in order to do this now, I'm gonna label all the equal angles with starting with this angle. Now, obviously, there's a isosceles triangle, BCD. So these two angles are equal. And then by the remember that the one of the most important angle theorems in a circle is the one with the arc, which means that this angle equals this angle because they all face the same arc. And so that's very important. Also, this angle here, angle B, the one we started with, also equals this angle also by the arc. And this angle is an isosceles triangle, ACD, so it equals this angle. And we basically like did like a lot of angles here that are equal, and there's like almost no other angles you can do. So for now, let's just look at this diagram. Wait, I think this angle here is also equal to this angle. I missed that. Okay, so now if we look at the diagram, it's going to look like a lot of angle bisectors, but that doesn't really matter. What really matters is that if you actually look at the conditions, we now know the angle ratio. The angle ratio is 1 to 2 because this is one angle and this is two angles because, well, the angles marked in the large things are equal. And so this is great. We know the angles, and therefore we can find out the angles. And this is actually kind of the easiest part because like we know the ratio. And you can let angle A equal theta, angle B equal 2 theta, and angle C equal 4 theta for convenience. And you can find that 7 theta equals 180 degrees by the sum of the angles. And so theta equals 180 over 7. And it asks for the angle of B. Angle of B equals 2 theta equals 360 over 7. And it asks for this number over here, which is 7. So yeah. Is there any questions? Okay, I think that's a no then. Okay, there's no questions, I hope. Okay, that's it for the third problem.
Okay, yes. Thank you, Edward, for the clear explanations. And then now we will move on to questions 4 and 5. Okay. Here is question 4. I saw many people solve question 4.
Alex, eyes on me, please.
All right, yes. Okay. I saw many people solve question 4. How many of you actually did a rigorous approach to this problem? If anyone wants to present their method, they can explain it to everyone. Since no one wants to present, then I guess I'll present the method. So number 4 uses something called invariance. Let me quickly get the pen. So invariance. So invariance are it's basically some number, it's some expression that stays the same after you apply all of the operations. That remains constant after applying any operation. So let's take a look at what operations we have in this problem. Actually, let's first look at this problem itself. So we have 13 dragons, 14 unicorns, 17 phoenix. An operation is when two creatures meet and then we turn them both into the third species. So this could be one dragon and one unicorn turned into two phoenix. It could be one unicorn and one phoenix turned into two dragons. Or it could be one dragon and one phoenix turned into two unicorns. So these are our set of operations. These are the operations we have here. Okay, so now we want to find an expression that remains invariant. Okay, so let us say we have let's say we have A, B, and C, where A is the number of dragons. This is the number of dragons. B will be the number of phoenixes. And C will be the number of, B is the number of unicorns. This doesn't really matter, but okay. And C is the number of phoenixes. And now our invariant, it will be A, it will actually just be B, 0A plus 1B plus 2C. And actually, this is our full invariant. The remainder of this expression mod 3 always remains constant after any operation. So in order to prove this, we will quickly take a look at what each operation will do. So let's say if we have the operation that turns one dragon and one unicorn into two phoenixes. So then in this case, basically what this operation means is just A minus 1, B minus 1, and C plus 2. So if we plug this new triple of A, B, and C into our expression, what we would get is B minus 1 plus 2 times C plus 2. And this is equal to B plus 2C plus 3, which is actually equivalent to our original, congruent to our original expression mod 3. And then after that, we can also check the other two operations. If a dragon and a phoenix becomes two unicorns, or a phoenix and a unicorn turn into two dragons. In all of these cases, we will see that 0A plus 1B plus 2C remains constant mod 3. Okay, so now we have just said that 0A plus 1B plus 2C mod 3 does not change after any operations. Okay, so now we look at our initial and final states. So our initial state is we have A equals to 13, B equals to 15, and C equals to 17. These are given in the problem. So then the remainder here, so then the invariant, like the expression evaluated with these A, B, and C, it would be 15 plus 32, which is congruent to 15 plus 34, 34, which is congruent to 1 mod 3. And meanwhile, what we want to achieve, okay.
Oh, Alex, can you explain where the 34 come from?
Plug in the numbers. Because it's just 2 times 17. When you plug these A, B, and C into 0A plus 1B plus 2C. So now what we want to achieve is all creatures same. So all creatures same. So this could be, wait, why can I not annotate? Okay, this can be either, so this can be either one of these cases, as in A, B, C equals to 45, 0, 0, or it could be 0, 45, 0, or 0, 0, 45. So, but either way, when we evaluate this expression, if for any of these three triples, we get that 0A plus 1B plus 2C will now be congruent to 0 mod 3. So this means that in our final case, the invariant we will be having is 0 mod 3, but then we started with a 1 mod 3. So it is impossible to reach this 0 mod 3 starting from a 1 mod 3 because we just said that that expression stays the same after all operations. So thus the answer is -1 because it is impossible to reach the final state. It is impossible to reach the final state since the values of the expression values of 0a plus 1b plus 0a plus b plus 2c. Since the values are different in the initial and final state. But initial and final states. Okay, does everyone understand this method? Okay, yeah. So this is the method for question 4. If anyone has any questions about this, like you can feel free to ask.
Alex, can you talk about the invariant?
I just explained. Oh yeah, and actually for number 4, I have another approach. This because the invariant we used here in this question, we used the invariant 0a plus 1b plus 2c. But it may but this invariant sometimes it may be hard to think about because it is not symmetric. So I have another idea for an invariant, which is a squared plus b squared plus c squared mod 3. And we will prove that this remains constant because what any operation does is it removes one animal of like a 2 species and adds 2 animals to the 3rd species. A minus 1, B minus 1, and C plus 2. So why don't we evaluate it with these new values? A minus 1 squared plus B minus 1 squared plus C plus 2 squared. This is equal to A squared plus B squared plus C squared minus 2A minus 2B plus 4C plus 6. And this is congruent to A squared plus B squared plus C squared plus A plus B plus C mod 3. And since in the question we have 45 animals, so A plus B plus C, this is equal to 45. So this is actually just congruent to A squared plus B squared plus C squared mod 3. Yeah, so this is another invariant which we can also use for this problem, and it sometimes might be easy to think of because it's more symmetric. And also, oftentimes, for many different problems, you'll see invariance with just the sum of the squares of a bunch of values, since sometimes this has some nice properties. Okay, moving on, let's go to question 5. I will copy paste the graph. Did anyone solve question 5? This question was meant to be a bonus problem, so it's understandable if like many of you had difficulties doing this problem. It was actually quite hard. Okay. Does anyone have any idea? Okay, then I'll explain my method. First of all, let's look at this original. Wait, actually, this graph has already been modified. It has like we've added some lines onto it. So, but first of all, what we do is in order to get segment EI, EI is actually a parallel shift of segment AC. So AC is shifted to EI. And then BD is also parallelly shifted to EH. Over here, as mentioned in the problem, E is the midpoint of this base. F is the midpoint of the other base. Also, could someone please not select this image? well, I don't know what happened. Okay, but yeah. But then now over here, but since this is now a parallel shift, what we have is that now AEIC and BDHE, these are parallelograms. Since this is parallel shift, because the two pairs of opposite sides are parallel. So that's EI is equal to AC. And we also have that EH is equal to BD. This was 25 and EI equals AC equals to 31. Okay, so now because we have all of this, and then meanwhile, the other thing we get is that because of the, also like using the same thing as earlier, because AEIC and BDHE are parallelograms, we have that HD equals to EB and AE is equal to CI. So thus, HF is equal to HD plus DF, which is equal to DF plus EB. And because F and E were the midpoints, like because earlier as given in the problem, DF is equal to FC and EB is equal to EA. And EA was also equal to CI. So this is equal to FC plus CI equals to FI. So now what we actually have is that HF is equal to Fi. So F is the midpoint of HI. F is the midpoint of HI. Okay. And then I will copy paste the graph again because it looks like okay, and then now over here, we also notice another property. And this property is that triangle, that the area of triangle EHI is equal to the area of ABCD. And the reason for this is that, remember, we have that AE equals to EB equals to HD equals to CI. So marked in blue are the pairs of, marked in blue and red are the pairs of triangles. So because these triangles are equal, so this can be used to prove that the area of triangle EHI is equal to the area of ABCD. Okay, I will quickly prove this. So the area of triangle EHI is equal to the area of ABCD plus, I'm just going to call this one blue, blue, and red, red. This is equal to plus blue, plus red, minus blue, minus red. So then these obviously cancel out. So that's leaving us with triangle EHI is equal to the area of ABCD. Okay, now that we have all this, then we will continue. But now the graph is very simplified because instead of needing to find the area of ABCD, what we are now left with is finding the area of EHI. And we have already found the length of EHI and the length of the median. Okay, so in order to find the length of EHI, there are many ways. So one way is we first double the median. So our approach is called double the median. So when you double the median, you double EF to a point. You double the, I need to erase. Okay, so you double the median EF to a point F prime. And because EF is equal to F prime and HF is equal to Fi, thus we have that triangle, thus we have a pair of congruent triangles here. Triangle EFH is congruent to triangle FI, F prime. And then with this, what we now have is that F prime I is thus equal to EH, equal to 25. Now, so we have F prime I is equal to EH equals to 25. And these two are technically also parallel, but that's not really relevant in this problem. So what's more important is that because these two that the area of triangle EFH is equal to the area of triangle FI, F prime. So now what we can get is that the area of EHI is equal to the area of EIF prime. And now EIF prime, so now we have again simplified the problem. So EIF prime in this triangle, we already have that EI is equal to 31, FI is equal to 25, and EF is equal to 2 times 14, which is 28. So now this remaining problem just remains, what is to find out the area of this. And then luckily we already have something known as Heron's theorem to find this area. So Heron's formula, I will write out the statement of Heron's formula. So over here, given any triangle with side lengths A, B, and C, the area is equal to square root of S times S minus A, S minus B, S minus C, where S is defined to be the semi-perimeter. So where S is equal to A plus B plus C over 2. So now in order to find the area of this triangle, we can directly apply Heron's formula. So in this case, the S is equal to 31 plus 25 plus 28 over 2. This is a 31 plus 53 over 2, 84, 42. So S is 42, and then the area is now going to be 42 times 42 minus 25 times 42 minus 28 times 42 minus 31. And then by calculating this and simplifying, eventually we get that this is equal to 14 root 561. So thus our final answer is equal to 14 plus 561 equals to 575. Yes. Okay, so this is how we do number 5. So does anyone have any questions about this?
Okay, I think it's very late. It's already 8:45, so we're gonna end the meeting right now. And the result will be released like by the end of the week, and we will soon know who will be the first 3 winners. And the winners will
Also
be
be
rewarded.
prizes.
Yeah, will be priced with like, the Amazon gift cards and also the t-shirts with our, specially designed logos. Yeah. Okay, so have a good luck on tomorrow's AMC 10-12 exam, everyone, and have a good rest before the exam. So